How many engineers do we have in the audience? Faculty, wannabes? Wow. Businessmen, businesswomen? Architects? Any architects? How about attorneys? All right. People in professions like these are often called upon to provide ballpark estimates of what something might cost. You do this to see if the project is technically feasible and its cost is somewhere close to what the customer wants to spend before going forward with it. It's done all the time. What I have done is develop just such a ballpark estimate for what it would take to run the entire U.S. economy on solar energy. That is the subject of this presentation. Now, why am I doing this? Well, because whenever the subject of renewable energy comes up, the conversation usually turns to solar, and you hear statements like this one. Now, this happens to be true. The planet does receive enough energy from the sun in about an hour or so to run the entire global economy for 1 year. You then ask yourself, why can't we just capture the energy from the sun and solve our energy problems that way? Well, are we anywhere close to being able to do this? To get at this question, I have constructed a little thought experiment. Here it is. Let's suppose that we convert the entire American economy to all electric, and we produce all of the electricity to power it from a solar facility. In other words, we stop burning carbon and capture the sun. What would this solar plant look like, and how much would it cost? First, we need to know how much electricity our solar plant must generate. The Lawrence Livermore National Laboratory has developed this analysis of the sources and uses of energy. It calculates the energy content of all of the fuels that drive the U.S. economy, shown here on the left. For example, they take the amount of coal consumed and multiply by the BTUs per ton of coal and so on. Add these up and the total is 95 quadrillion BTUs. That's 95, the number 95 followed by 15 zeros, or 95 quads as they call them. This is the total energy consumed by the U.S. economy in 1 year. Now, some of this energy is converted into electricity, which is simply another form of energy. You see it here. This is some coal, some natural gas, goes up here to this little block, which represents the electric power industry. And then that electric power, represented by this bar, is delivered into the economy, which is represented by this red box. The electricity plus the remaining forms of energy, for instance, down here, see all this petroleum, for instance, goes directly into the economy, or petroleum and byproducts. That electricity plus the remaining forms of energy constitute the energy input to the economy, symbolized by the 4 pink boxes. These boxes represent the 4 main sectors of the U.S. economy: residential, commercial, industrial, and transportation. Total demand for energy from these sectors in the box is about 70 quadrillion BTUs, or quads, per year. This then is the amount of energy we must generate from our solar facility. Now, before we go on, a couple of quick comments about this chart. Notice that 86% of all the energy we consume currently comes from fossilized carbon, but only 0.2% currently comes from the sun. Now, this is as of 2012. Over here on the right, because as you know, all you engineers know that you can't destroy energy, this is kind of a sources and uses of energy. It's kind of like a cash flow statement for the business people. Sources and uses of cash, same thing. Can't destroy cash, can't destroy energy. So what the energy you start with has to be the energy that you end up with. And it turns out that the energy either produces useful work, which is represented by this box, or it is lost. or rejected, as they call it. Of all the energy input to our economy, 61% is rejected or lost. Only 39% ends up providing useful work. So here's our objective. First, design a solar power plant that reliably delivers the electric energy equivalent of 70 quads to run the U.S. economy for 1 year, or 56 times 10 to the 12th watt hours, or 56 terawatt hours of electricity per day. Our solar facility would consist of a photovoltaic panel and a battery. The PV panel would generate enough electricity during the day to power the daytime economy and charge the battery. And the battery would power the economy at night. Second, estimate the cost of building the whole thing. Let's assume the following. The PV panel would be spread out in the southwestern states because that is the sunniest place in America. And secondly, we build in a 50% safety factor to handle any contingency. If we start with a demand of 56 terawatt hours of electricity per day and add a 50% safety factor, we find we'll then need a system that can produce about 83 terawatt hours per day. Let's further assume that the nighttime demand will be half of that, or 41 terawatt hours. Now, keep in mind that all of these are just approximations. I know that the nighttime demand is less than the daytime demand, but at this point, I don't care. This is a back of the envelope analysis. Okay, here's what these things look like, a typical solar power plant. Notice that the footprint of the power plant is greater than the size of the PV panel because there is a lot of open space between the panels, along with access roads and so on. So we know what it looks like. How much space would it consume? The easiest way to estimate the footprint of a solar facility of this size is to look at the operating experience of existing solar power plants. Here are several examples. The sample shows that the actual output is in the 70 to 170 watt hours per day per square meter range. Let's assume that our plant's performance will be in the neighborhood of the plant at Nellis Air Force Base and produce about 150 watt hours per day per square meter. If we assume 150 watt hours per day per square meter for our power plant, then its footprint would be about 210,000 square miles. And just for your reference, the land area of the United States is about 4 million square miles, so that would be about 5% of the total land area of the U.S. So we have the power plant. Let's move on to the battery. For the battery, we will use technology known as pumped storage hydro. Here's a schematic of one of these plants. This method stores energy in the form of potential energy of water that's pumped from a lower elevation reservoir, which is down here, to a higher elevation reservoir that's up here. In our example, excess electric power from our solar facility that is produced during the day would be used to run the pumps and fill the upper reservoir, pumping water from the lower reservoir through these pipes up the upper reservoir during the day. Then, at night, the stored water would be released through turbines to produce the electricity that would run the nighttime economy. So now you essentially have a little hydroelectric power plant runs down these pipes through the power plant chamber into the lower reservoir. Here's an example of one of these facilities. This one is on the eastern shore of Lake Michigan. The lower reservoir is Lake Michigan. Here it is right down here. And the upper reservoir is a man-made lake right up here. The drop, as it is called, that is the height of the upper versus the lower reservoir, is about 350 feet. And you know, this is located along the eastern edge, you know, these sand dunes, the bluffs that have been naturally formed over there. Here's another one. In this case, the lower reservoir is a river. There's the river. It's been dammed up, and here's the lower reservoir. And the upper is a man-made lake. Notice that all the workings of this facility, pipes, pumps, power plant, etc., are buried in the hill that separates the two. So you basically can't see any of it. And here's another one. In this case, the lower reservoir is the ocean. This is proven technology. Pump storage hydro is the largest capacity form of grid energy storage available. As of March 2012, the Electric Power Research Institute reports that pump storage hydro accounts for more than 99% of the bulk electric energy storage capacity worldwide, representing around 120,000 megawatts. There are about 50 pump storage plants with more than 1,000 megawatts of capacity in operation around the world. In 2009, the United States had about 21,000 megawatts or 21 gigawatts of pump storage generating capacity. Many of these plants have been built during the 1970s and have therefore been operating for more than 30 years. Now, here are two good examples of pumped hydroelectric storage in the U.S. The first, the one we just looked at, the facility at Ludington, Michigan, is built on a bluff overlooking the east shore of Lake Michigan. It was constructed in 1969-1973. The Bath County facility is located in the northern corner of Bath County, Virginia, in the Allegheny Mountains. It was constructed in 1975 through 1985 and is currently the largest pump storage facility in the world. Here are the relevant specs. For the purposes of this analysis, we assume that the nighttime energy demand would be about half the daily demand, or 41 terawatt hours. If we fulfill this requirement with pump storage, we would need about 1,000 facilities like Bath County, Virginia, or about 1,640 like Ludington, Michigan. Given the footprint of each of these facilities as shown, the total footprint would be about 1,300 square miles for the Bath County option and about double that for the Ludington option. What would all this cost? Assuming today's technology and today's cost, this power system would cost about $70 trillion to build. Let's first the PV panel. The Energy Information Administration, which is a division of the Energy Department, reports that the cost to build a photovoltaic power plant of 150 megawatt capacity averaged $3.90 a watt of capacity in 2012. The capacity of a solar power plant that could generate the required 83 terawatt hours of electricity would be about 17 terawatts. The installed front-end cost of our facility would therefore be $3.90 times 17 terawatts, or about $66 trillion. For the battery, if we use the actual construction costs of the two pump storage hydro projects that I showed you earlier, the Bath County option would cost a total of about $5 trillion, and the Ludington option would cost about $3.5 trillion. So let's say the cost here would be $4 trillion. You add those two together, and you get $70 trillion. Now notice, this is the cost today to build this system. The capital expense, or CapEx. It is not the cost to operate it, nor is it the so-called levelized cost, or a life cycle cost of these facilities. So, to summarize, to power America with today's technology and today's cost, we would build first a solar power plant using photovoltaic panels, giving it a footprint of approximately 210,000 square miles, or about 5% of the land area of the U.S., and costing about $66 trillion to build. The battery would be pumped storage hydro with a footprint of approximately 2,000 square miles, costing about $4 trillion to build, total about $70 trillion. Now, a few comments about all of this. Putting the PV power facility in the Southwest makes sense from a solar energy point of view because this is the sunniest part of America. This is a map that shows solar intensity. Excuse me. This is a map that shows solar intensity, the annual direct normal irradiance, as they call it, across the U.S. As you can see, this is where most of the existing projects are located. Each one of these little dots represents one of these plants. They're mostly located down here in the Southwest, although there is at least a few up here in Illinois. But this strategy has two problems. First, the Southwest, defined as the Southern California, starting about here, through the southern tip of Nevada around Las Vegas, Arizona plus New Mexico plus the panhandles of Oklahoma and Texas, which is generally this area right here, constitutes about 400,000 square miles. Our facility would therefore cover about 50% of it. Secondly, if a major storm covered most or worse all of this, electrical output would drop dramatically and the whole country would suffer. We basically have a nationwide brownout. Putting our PV power plant in the southern states, defined as the Southwest, all of this, basically going east, plus all of the states east to the Atlantic coast, so generally along this line, south, alleviates the storm risk scenario a little bit, but puts much of the panel in states that are not as sunny as the Southwest, and so our PV panel facility would have to be larger to account for that. Even without this expansion, it would occupy about 22% of it. Now, some people would say that much of the land in these states is empty. Nobody lives there. But others would say that it's wilderness, or a grazing land, or farmland. It's safe to say that either the Southwest or the southern state strategy would provoke some real pushback. Well, how about PV panels on houses? A popular concept these days, but this is not the answer. There are about 89 million houses in the United States. If the owners of every one of them installed 1,000 square feet of PV panel on their roof, that's a panel that's 20 feet by 50 feet. If every one of them did that, the total area would be about 3,200 square miles, a lot of PV panel, but a small percentage of the needed area. There are 89 million houses in the United States. Currently, there are about 600,000 that have PV panels of some size on their roofs. It's 0.6%. Now, the capital cost of PV power plants is falling as the cost of PV panels drops. Today, PV panels cost about 74 cents a watt, 1/100th of the cost in 1977. But the PV panel is only one component of the total cost of a complete solar power plant. The so-called non-module costs, for example, inverters, mounting hardware, construction labor, permitting and fees, overhead, taxes, installer profit, etc., now make up at least 2/3 of the total installed cost of a typical plant. Further reductions in total cost will require significant reductions in these non-module costs. Now you might say, well, where did you get these costs? Maybe the real problem is your costs are too high. Other people say that the CapEx of these power plants is much lower. Well, my CapEx cost for a PV power plant comes from the EIA, the Energy Information Administration. It's a division of the Energy Department, and their numbers are based on projects that have been completed in 2013. You're right that there are other estimates out there that are lower. For example, Lazard, which is an investment banker, quotes a much lower number, but it is based on projections for projects that have just started. Remember that this whole exercise is based on today's technology and today's costs as defined by projects that are currently in production. Now here's a big issue. The battery stores only one night's worth of electricity. Well, what happens if a large weather system covers most of the PV panel? It is not unusual for large parts of the country to be covered by clouds. As a matter of fact, last week at some point, I looked at the Weather Underground cloud map of the United States. I thought about 90% of the country was covered by clouds. When was the last time the sun shined in Chicago, for example? Well, what happens then? Well, to deal with that, we would need a backup system. And since it seems entirely possible that for some period of time, all of the PV panel would be covered by clouds, and that the electrical output of our solar system would drop to, say, 20 to 30% of its capacity, the backup system must be big enough to supply 70 to 80% of the energy that we need to run the economy. In other words, the backup system would basically be the electric power system we have today. You know, when you think about backup systems, there's one of two ways you can go about it. You can buy a backup, let's say you're talking about your house, if you want to buy a generator, and you want to buy a system that keeps the whole organization running for a relatively short period of time until you can shut down the operation, do a controlled shutdown, so that you can get everybody out of the elevators, you can save all of your files, you can protect all your equipment and so on, and then everything shuts down. So the whole organization for a very short period of time. The other approach is to protect just a small piece of the organization for a long period of time. So if in your house, for instance, you'd buy a generator that could run your refrigerator, that could run your hot water heater and a few other things, and keep it running for a week or so until the power comes back on. Well, you can't do that with the economy. You can't simply send out a text message to 315 million people that we're going to shut the economy down in an hour. Nor can you tell these people, okay, we're going to shut it down to about 10 or 20% of the most essential services, police, fire, hospitals, maybe some streetlights, everything else comes down. You're just going to have to deal with that until the sun starts shining again. You can't do that. So you have to be able to back up the whole economy. Now, the other thing to think about is, and you notice I have question marks here because I'm just sort of proposing this in a way. I'd be kind of interested in how you all respond to all this. Right now, today, about 20% of the energy we use comes in the form of electricity. So if we're going to electrify the whole economy and run everything on electricity, we essentially have to quintuple the amount of energy, electricity we produce to run the whole economy. So let's suppose that we need a backup system. Well, if you needed a backup system to run maybe 80% of it, you'd basically then need a backup power system that looked like today's system that would be 4 times bigger than today's system. So the electric power industry would be 4 times bigger than it is today, and that would be your backup system. So you'd have a primary system, that's the solar energy system, that would be backed up by an electric power system, basically the electric power industry, ComEd, and so on, that would be 4 times bigger than it is today. Now, building the solar power plant is not the only cost of capturing the sun. For example, electrifying the economy. We simply assumed at the beginning that the entire economy had to be electrified so that all energy is now supplied in the form of electricity. But this in itself would be an enormous project. By far the largest part of it would involve the electrification of the transport sector. The chart I showed you earlier shows that transportation is the largest user of energy, about 38%, and that almost all of it comes in the form of petroleum. Electrifying this sector would mean abandoning the internal combustion engine and converting to electricity all cars, buses, trucks, especially tractor trailers, ships, and the entire railroad network. We would also have to rebuild and expand the entire national electric grid. Today, power plants are located close to the user. Major cities, for example, Chicago, are surrounded by a network of power plants. Current grid technology limits the distance that electricity can be transported to about 300 miles. Our new solar system, however, would locate the power plants where the sun shines the most. So in theory, much of it would be located in the southwest. This means that the solar-based grid would be much larger, and employ different technology than present because it must transport electricity much larger distances, for example, from Arizona to New Jersey. Finally, we would have to develop a computer network to control the whole system, the so-called smart grid. Work being done right here. The solar grid must be able to react to changes in the weather. Suppose we adopt the southern states strategy, so we position all the grid across the southern states. Further, suppose that on Monday, the southwest is clear and the southeast is cloudy. On that day, huge amounts of electricity must move generally west to east. Then suppose that on Tuesday, the following day, the southwest is cloudy and the southeast is clear. On that day, huge amounts of the electricity must move generally east to west. This will be happening every day as weather systems move across America. The grid and control systems to handle this do not today exist. Finally, as always, this emerging technology must proceed against competition from the incumbent. In this case, the long-term competition is likely to be gas. To see how tough this will be, consider this. My back-of-the-envelope design for solar PV power features electricity only when the sun shines, so you need a battery. Plus, it's all susceptible to the weather, and the total cost is about $70 trillion to build it. A gas-fired power plant, to produce the same results, would produce electricity rain or shine, day or night, so no batteries are needed, and the total cost would be about $4 trillion. This proposal is about 17 times the cost of the gas alternative. So now you say, so what? Sure, there are problems here. What difference does it make? We've done big projects with big risks before. And you're right. America is certainly capable of successfully sustaining large projects over long periods of time that require solutions to major engineering problems. 3 examples are the Manhattan Project. The project to build the first atomic bomb spanned 1942 to 1946 and cost about $26 billion in today's money. Project Apollo. The project that put the first man on the moon spanned 1961 to 1972 and cost about $130 billion in today's money. The Interstate Highway System. This was, at the time, the largest public works project in our history and still might be. It was authorized in 1956 and was completed 35 years later at a cost of about $500 billion in today's money. 3 very successful projects, but none of them even approaches the scale of what we're talking about here. So what did we learn from these projects? Maybe there are some important lessons here. What were the keys to their success? Number 1, a perceived threat or reward that leads to public acceptance. The Manhattan Project and Apollo Project were both responses to perceived threats, which compelled policymaker support for these initiatives. The Interstate Highway System was perceived as an enormous jobs program that would also produce a big jump in economic productivity. Secondly, a clear goal. Each product had a clear goal. Build the bomb, put a man on the moon. By the end of 1969, build the Interstate Highway System. Number 3, government money that ensures success. All 3 projects were funded by the government. For example, the Manhattan Project consumed about 1% of the federal budget during its life, and Project Apollo consumed about 2% during its life. The Interstate Highway System was self-funded via a gas tax that is now 18.4 cents per gallon. So how does our solar project score on these 3 success factors? Perceived threat or reward. Well, climate change and or the exhaustion of fossil fuels. But does the American public buy into this? Recent polls suggest that it does not. Clear goal. Well, electrify the U.S. economy, generate the electricity with a solar-based system. But whereas the Interstate Highway System for example, generated huge benefits to Americans, it is not clear if there are any near-term economic benefits from, for example, converting transportation from carbon to solar-produced electricity. And finally, government money to ensure success. The government's role in all three projects was to provide the funding. But given the huge amounts of money required and the fiscal shape in which governments at all levels find themselves, governments today are in no position to fund this entire project. So what to do? Well, here's what I propose. I call it Plan A. The reason I call it Plan A is I frankly hope that you all can come up with Plan B, C, D, and so on, so that eventually when we get to Plan Q, we'll have something that actually works. First of all, more research and development is required to do two things. We need to double the efficiency of PV panels. The current PV panels that are used in these plants convert only about 15 to 20% of all the sun's energy into electricity. We have to double that to 30 to 40%. Secondly, we have to reduce by 1/2 the cost of building one of these PV power plants. Success in both A and B would effectively reduce the cost of the PV power generation system to 1/4 of the current estimate, approximately, or about $15 trillion. When these are both accomplished, but only then, raise the capital to build the system by imposing a $1.25 tax on each gallon of gasoline and diesel fuel. Americans currently burn about 135 billion gallons of fuel, so the tax would bring in about $170 billion a year. Note that this is about 1% of current GDP. At this rate, the whole system, power generation plus the batteries, assuming these improvements in current technology and current cost and no others, this project would take about 100 years to build. Finally, as with any energy plan, we must continue to work on energy efficiency. The chart above shows that I showed you in the beginning, shows that of the 70 quads of energy supplied to the economy, about 47% of them are rejected or lost. Improving energy efficiency, as measured by the number of BTUs per dollar of GDP, is an absolute must, regardless of the way forward. So a final comment. The intent of this exercise is to arrive at a ballpark estimate of what it would take to stop burning fossilized carbon and capture the sun. There is obviously a large margin of error, plus or minus, in all of it. But even if you set aside the whole issue of climate change, one thing is certain. Eventually, we Homo sapiens will consume all of the planet's supply of fossilized carbon. Long before that time, we must develop an alternative to burning that carbon. It's a good bet that solar will eventually be a major part of our energy equation. The good news about the sun is that it is, for all practical purposes, an inexhaustible source of energy. It's free, and it's available to everyone. No country can seize control of the sun and deny it to others. But it is also true that solar power today supplies only about 0.2% of the energy to run the U.S. economy. To get where we want to go, that is to 100%, we need much better solar technology, much lower cost to build it. We must electrify the entire economy, including transportation, build a national grid with long-distance electricity transport, and a smart grid that cannot be hacked. Against stiff competition from low-cost fossilized carbon alternatives, for instance gas, the public's lack of interest, and the government's lack of money. Now, those of you wanting to chase down the provenance of the numbers and the calculations to get the results displayed here, I invite you to go to this website. It holds the article from which all of this is sprung. It includes about 40 endnotes, so this should explain everything. Thank you all for your time and attention.